And finally, to wrap up Chapter 3, we're going to be talking about derivatives of exponential and logarithmic functions. These include e to the x, a to the x, which can be any constant, ln of x, log base a to the x, and power rules for arbitrary real powers. Now, deriving e to the x, which is the Euler number, e raised to x, is perhaps one of the most interesting derivatives, and that's because something interesting happens. If we take the limit of h approaching 0 of e raised to the h minus 1 divided by h, we have this being equal to 1. Now, if we take the derivative of e to the x, we just get e to the x. And this is true no matter how many times you take the derivative of e to the x. It's a very unique function because it's its own derivative, so no matter what point you go on the graph e to the x, if you take the tangent line at that point, the slope of the tangent line will be equal to the y value at that point, which makes this very unique. Now, if we graph this number, if we graph the function y equals e to the x, we get this exponential growth graph. Now, just a quick reminder, e, also known as the Euler number, is a natural number, much like pi, or the golden ratio. It shows up a lot in several different phenomena, things ranging from radioactive decay all the way to compound interest. Like pi, it pops up in random places that you might not expect it and has some very unique properties, this being perhaps the most profound of those properties. When doing a calculus problem, it's always fun to encounter e to the x because it's so easy to deal with. Let's say we have a constant a raised to the x and we want to derivate it. Well, that would look a little something like this on the right-hand side. d dx of a to the u is equal to a to the u times ln of a du dx, which in the case of e would look something like this. If we have a constant a raised to the x, we can rewrite that as e raised to the x times ln of a. This relationship simplifies taking the derivative of a constant raised to a function. Otherwise, having to derive a function such as a raised to the x would be rather complicated. What happens if we take the derivative of ln of x, aka the natural log of x? Strangely, that just results in 1 over u du dx. Again, this relates to e. If we have y as being equal to ln of x, and we know that e raised to the I is equal to x, then taking the derivative of e with respect to y is equal to taking the derivative with respect to x of e raised to the y is just equal to taking the derivative of x, which of course is just 1. And if we have dy dx as being equal to 1 over e to the y, which we already said earlier is just x, as we can see up here, then dy dx is going to be simply equal to 1 over x. Now, again, it's not all that necessary to know how this was derived, but just know that if you see a situation in a problem where we have to take the derivative of a natural log of a function, it's just going to be equal to 1 over that function. Looks a little bit complicated, but it's really not that bad. So just to recap, if we see a natural log, a function within a natural log, and we take its derivative, then that's going to be equal to 1 over that function. Easy to overthink, but it's not that bad. And what about deriving a function that's inside of a log with a certain base a? Once again, a fairly simple process like we just talked about. We can use this relationship over here in the blue to assist us with our derivation. Now, this right here looks an awful lot like our chain rule that we were talking about earlier. We have 1 over a raised to the sine of x times ln of a, and then also the derivative of the inside function, which we can see right here. And this all simplifies down to, surprisingly, cosine of x. But once again, it's not totally necessary to see this whole process. We just have to remember that if we encounter a log with a base a in one of our problems, we have to remember to apply this formula right here. And finally, we have the power rule for arbitrary real powers. If u is a positive differentiable function of x and n is any real number, then u to the n is a differentiable function of x, and the following is true. Again, we have another variation of our power rule. This keeps popping up over and over again. And what does this all mean? Well, if we have a function like this, y is equal to x raised to the square root of 2, then the derivative of that is going to be the following. We can use our same power rule that we used before for any real numbers as long as u is a positive differentiable function of x, and n has to be a real number. So in short, this basically broadens the power rule to include exponents that are also square roots. Or, for example, if we had this composite function down here, where our exponent is pi, it still applies. The power rule would still apply, so we can pull it out in front here when taking the derivative, and just have a pi minus 1 here at the top, and then, of course, here we can see that they applied the chain rule as well. The derivative of the inside function times the derivative of the outside function. But don't overthink this. It's just basically saying that the power rule can apply to situations like this where our exponent is a square root or a number like pi, as long as the function inside that's being raised to that power is a positive differentiable function of x. So this is just an expansion on the definition of the power rule that we have talked about so many times before. And we are finished with chapter 3.9, dealing with derivatives of exponential and logarithmic functions. Just another few tools in your toolkit for taking derivatives of various functions. And with that, we also wrap up chapter 3, one of the longer chapters that we will be covering. We will cover chapter 4 next, which will go into quite a bit more detail with the example problems, applying what we have just learned.